Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this Sunday, the 8th of February 2026, to Seeing Changing Inside. So can you hear me out there in YouTube lands? Hello Chauxis down there in Australia, Overwound Games. Hi Marty Angel. Hi Artifact there in Germany. Bill Schwant over in the good old USA. Hello Estonias. We got some Scandinavian people joining us here. Forest Trouble 2088. Welcome. Cagliostro Felletta, great to have you here. Austin Sumroll, Everyday Alchemy is here as well. Wonderful. Ken Pratt, another great American there. John Coombs, wonderful. Hello. DRX7562, thank you for joining us. Gordon Doherty there in the UK. Great, we've got a representative from good old Blighty. Thank you for joining me, Stephen F. Let's rock indeed. Hi, Weedner, DWC, EBB 2421 from the Okanagan there in Canada. Great to have you here. Well, we have a good quorum, don't we? Hello, Zalepieno. Nick Moore again. We have another Brit in the house. Wonderful. Crypto Alchemist. Excellent. Wonderful. All over the world. Lovely. It is great to have you here. Now, I hope this works because they did something here and they rewired everything, so I haven't had internet for a couple of weeks. But now I'm on Wi-Fi. I'm sorry if it dies halfway through, but we'll do what we can. Anyway, we're going to look at some things that are going to be a focus of some of the project's work this year and partners that we are working with to bring practical technologies to the fore. So obviously you know that I have inspired and been inspired by one George Eagley, and I saw a verified version of his energy amplifier in New Mexico last year, and that was part of my journey after the conference there, Tesla Tech, in which I did a little bit of a jaunt, 2,500 miles, and during that I did some experimentation. And I met up with one Griffin Brock down in California. He was sick, he couldn't do the experiments with us, and we're going to look at that. We've actually shown some of the data from those experiments. And I went down and visited him after he got over his illness and picked up a bunch of tubes to bring them back here to Europe so that they could be tested in a replication. And we're going to look at some exciting new developments from that. It is amazing to be able to play a role in trying to find a way to get these technologies into practical use. And I feel like the luckiest guy in the world right now to be able to move from theoretical understanding into devices that could have implications for healthcare, for radiation remediation, for energy generation with the work that the project is doing, and myself with Binjuan Huang in Taipei in Taiwan. So we're going to look at a little bit about things that we're going to do moving forward in various aspects. So thank you very much for joining me. You may be wondering why I am showing this insignia of the United States Navy and what I mean by seeing and changing inside. Well, don't worry, you will find out. Okay, so this was the Griffin Brock device that I worked with in Alan Goldwater's Magic Sound Lab there in California, in Santa Cruz, and I will be having the pleasure of his company again, going over there, and we are going to do, ready for this, a replication of the most senior member of our field's premier experiment, that is Dr. Edmund Storms. So it is high honor that we can have the opportunity to replicate this man's work with his full cooperation. This former Los Alamos National Laboratory researcher who obviously you may or may not know developed the nuclear rocket and other things in his term there, and has been a stalwart in this field, but he handed over his equipment and so forth and is in residential care, and he reached out to Alan, and Alan asked, shall we do this? And I gave it full endorsement, and I have to thank Ryan Hunt for agreeing. So we are going to be investing most of the available funds the project has in this replication coming up, and I think it would be amazing if we can replicate that before he passes on, so he knows a third party has done a full-on replication. Whilst I'm over there, I've got another sample of the inside of one of Binzhen Huang's reactors, the one that gave us the flux capacitor video and all that analysis that really showed us what the process is and how it captures matter and what it does to that matter. And we're going to be doing further analysis of that. However, what I want to do is something that we learned from this good fellow here, Dr. Takaaki Matsumoto, and that was, I think in 1991 or 1990, he took one of his samples from his experiments and he put that in a tube attached to a residual gas analyzer, and he heated that up to see the off-gassing. Now, to the best of my knowledge, this is the only person that has ever done this process, but we are going to do that process too. And I also hope to I've got about a litre of the fluid from a reactor by Binzhen Huang. What I'm going to do is learn from Paul Harris, the Alchemy of Prague. I watched him go through his process of distillation to leave the salts behind in the process of traditional alchemy. And what I'm going to do is I'm going to use the same kind of technology. I'm going to use a sand bath on an induction heater in order to ensure that I can maintain a specific temperature. And I'm going to distill off the fluids and leave behind the salts from, or any potential salts that are there from the reactor of Binzhen Huang, and then look at that under the SEM. And then we're also going to take the spirits, the fluid that is boiled off, and put that through the mass spectrometer as well, and then also heat the salts as well. So these are the things I'd like to achieve. It's a lot to achieve, because what I also want to do is do another experiment that of the same kind that I did when Griffin was not with us because of his illness, where we tried the exposure of these radioisotopes. And if you remember, I talked about this recently, and I'm going to go back to that presentation for those people that missed it. But essentially, I've been accepted for 2 oral presentations in Bologna at the end of this month, and I'm going to show you what those 2 presentations are going to be subjected on just now. The first one will be in large part referring to Binzhen Huang's reactor, and so I will read you the abstract now. So I thanks to the organising committee of ICMNS, the International Workshop for Hydrogen-Loaded Metals in Italy at the end of this month. And what I'm calling this is Predictable Non-Natural Isotope Synthesis and its Relationship to Excess Heat. And we're going to come back to this little clip here. On April the 23rd, 1998, Professor George Miley asked Professor Martin Fleischmann, "What I wanted to ask you about, since you're talking about the future, you've left the whole field of transmutations out. What is your view of that?" And Martin's conclusion, and we're going to show his full commentary in a little while for those that haven't seen the video, is, "I think if you have a distribution of isotopes which are not natural, then you really have to believe it. That is to say, believe that you're getting transmutation and that is a nuclear process." Okay. So On the 14th of June 2021, it was predicted, that by my good self, that in the heat-producing cavitation reactor of Binwen Huang et al., the observed carbon that he observed, and he had reported in previous presentation, would be the result of producing first 17 oxygen from a proton and, well, in fact, an atomic hydrogen and 16 oxygen, with 17 oxygen subsequently yielding carbon and neon. It was subsequently found that the most likely reactions, according to the hypothesis, and the hypothesis is essentially squeezing stuff into a small box, and that goes into a coherent state, and the coherent matter interactions yield, and it was observed to yield 17 oxygen and neon 22. In fact, that shouldn't be 17 oxygen. I need to change that. It should be 12 carbon and neon 22. So I need to change that. Were observed, which is, so this here should be 12 carbon, not 17 oxygen. It produces 17 oxygen first. Anyway, were observed, which is interesting, and these are both the rarest isotopes of their respective elements. No, I have written that correctly. So basically, the most likely reactions, according to the hypothesis, yield this rare isotope of oxygen and this rare isotope of neon, and these are both the rarest isotopes of their respective elements. This understanding allowed a new evaluation of other observations, including those of Sundaresan and Bockris. So Bockris was the world's leading electrochemist and at Texas A&M University, and Sundaresan was on secondment from the Babaratomic Research Center in India. And also, I'm going to suggest the 2024 observations of Gambarale and Modenese. And Gambarale, as I said before, worked under the coherent ground state of water expert and discoverer of Giuliano Preparata. And Modenese worked with a certain anti-gravity researcher from Russia that lives in Finland. The simple logic of the predictive approach used will be reviewed and shown to explain the excess heat and rare isotope distributions observed in these experiments, as well as potentially why we see particularly abundant isotopes of certain elements in nature. So that's the first of the talks that I will do for about half an hour. And you'll recognize that I've talked through several of those subjects in recent weeks, so I've been preparing this for a while. The second one is developing practical technologies for radionuclide remediation. In a world increasingly demanding new carbon-free energy sources, a major stumbling block to commissioning new nuclear power generation is the subject of radioactive waste. In 1957, Ivan Stepanovich Filamenko claimed production of excess energy alongside hydrogen, helium, and oxygen isotopes using a palladium heavy water reactor. Due to its operating temperature of 1150 degrees C, it was called warm fusion. Now, I want you to hold that in mind as we look at something a little bit down the line that the US Navy did about a quarter of a century ago. Due to its operating temperature of 1150 degrees C, it was called warm fusion. Furthermore, it was reported that the apparatus emitted some form of radiation that reduced the half-lives of radioactive radionuclides and or suppressed radioactivity. And this phrase here, this understanding, was something that I learned when I was preparing for the translation of Parkhomov's book, Space, Earth, Human. That's Dr. Alexander Parkhomov of the Russian Academy of Sciences. And this stuck in my mind, and it was this thinking in correlation to the, thank you very much, Black Tie, for that £20, in correlation to the book I have over here, The Secrets of Cold War Technology by Jerry Vassilatos, where it was discussing that Tesla was working with this etheric matter and dark light, that, as he called it, and that he used aluminium, boron, beryllium, aluminium, or magnesium, not in that order, beryllium, magnesium, aluminium, and aluminium was the heaviest element he found produced clean etheric matter rays, and that he could produce these shadow graphs. And I thought this kind of radiation would be coming out of these reactors, and in part of that was because of what was claimed by Filamenenko. And so I suspect, I had this conversation with our colleague over in Canada, David, who was working on the Vega replications, and he went away and he found Griffin Brock, shared it with me, and I got very excited because I wanted to test this device. One, I wanted to test the electrode because I expected to see the magnetohydrodynamic structure on there, because I believe that it has to be there for it to come out, and we subsequently found that. And we're going to talk a little bit more about that later. Absolutely, thank you very, very much. Very kind of you. J Beach Loves, that's very kind. And also Algaz, thank you very, very much. It's really, really appreciated. So, yeah, so basically it's really, it's amazing, guys. I'm really, really stoked. It's really helped. Okay, so I kind of felt that he discovered this guy, Griffin Brock. We analyzed this electrode, and then I was convinced that this would be able to produce this kind of radiation, these neutral charge clusters, these neutral energy solitons that would be able to interact with radionuclides and potentially deactivate them to a degree. And in part, this was because of conversations I had with John Hutchison, where he was sent a radioactive sample by a radioactive sample supplier, and he applied his frequencies and process to it, sent it back, and that sample was reduced in radioactivity. And so there was a whole series of data that pointed me in a direction that, wow, this device, he's not talking about it, because what Griffin had done was he was replicating the shadowgraph technology of Nikola Tesla, and he's the first person at the time that he did it in about 120 plus years to have done that. And he also did it on video. He did it on video, so he could actually real time do this shadowgraph process. So that's the first time in history, but he was replicating the work of Nikola Tesla. And so I thought, well, this must be this etheric matter rays, this dark light, and I believe that these are these charge clusters that are neutral, and they should be able to go through radioactive material. And what we found was that indeed, in the initial test, that was done in California, I know I've already shared some of this already, so let me see if I can pull it up here. Yeah. So here is the overview here. You can see Alan the Wizard over here. We have the samples on this wooden block here that Alan fashioned up. This is the Desmotron tube. This is the resonant air coil, and this here is a 1920s diathermy unit. And here's a bit of a close-up. Here are the various radioactive samples. Now, we didn't have much time because he was sick. He sent it and it arrived 3 days later than we thought we could start. So we were really up against it. And so I piled all the samples in one without really thinking about their ferromagnetic nature. And I think this one or this one, it's ferromagnetic, and some of them are paramagnetic. So the clusters might bind to that. We know ferromagnetic materials they bind to because of Leonid Oritskyev's exploding metal foils, it binding to iron 57 sheet. We also know that it binds to iron in the work of Matsumoto. So the data is provisional, but I did what I could in the available time. And the fascinating thing about this device is it has these spark gaps. And the interesting thing about the spark gaps is that they are tungsten. And tungsten is one of these magic elements like aluminium that, whilst it probably is producing dirty etheric matter rays, tungsten, when you have these charge clusters striking between them, it has, in my view, the ability to enhance this production of these clusters, and I think they will be traveling through the wire. So I think it's not just that you are doing some magic in the actual tube. Some of the magic starts here, and it's interesting that, of course, this would be in the 1920s. And so this is the first spark gap diathermy unit, and it was invented around 1908 by German physician Karl Franz Nagelschmidt, who coined the term diathermy. In the early diathermy units, multiple spark gaps were connected in series as part of the high voltage circuit to generate the necessary high frequency currents for the therapeutic heating. This series configuration helped manage voltage breakdown and improve quenching in the spark-excited oscillator, similar designs in early radio transmitters. Now, what I spoke about in my Tesla Tech presentation, which I may edit and publish next Sunday, is that this series process of spark gaps was reported by Maury B. King in a presentation many years ago, and it turns out that that was never published by Ken Shoulders. And I tried to find it somewhere, and I could never find it anywhere. It was only mentioned as something that Ken Shoulders had said in this presentation. Well, when I was at Tesla Tech, I had a sit-down one-on-one for about 3.5 hours with Maury B. King, and then another several hours in the evening. Absolutely fantastic. And during that conversation, he told me that that was a personal one-to-one conversation with him and Ken Shoulders. And the nub of that conversation was that when you have a series of these spark gaps where one goes into the other, it actually amplifies the amount of charge clusters that you are producing. So the actual structure of a diathermy unit from the 1920s, in fact, from even early spark gaps, but I assume from 1908 potentially, was actually the arrangement that produced the most powerful spark and EVO production that Ken Shoulders had ever observed in terms of the production rate. So what you're seeing here is something which is more than 100, nearly 120 years old itself. But it is the arrangement largely, although it's not a small electrode into a big one, it's a big one into a big one. But this is not too dissimilar from the Eagley NG amplifier. In the Eagley NG amplifier, he has aluminium. I said in 2021 or 2022 in the Garden of Domus Patches, I said, George, you're going to need to use aluminium. The problem with aluminium, though, is it will transmute. But aluminium and tungsten are these two unique elements in the periodic table that either have the beautiful ability to fusion and fission in the case of aluminium, and fission mostly in the case of tungsten, but they are the most conductive elements that are paramagnetic, because gold, silver, and copper are all diamagnetic, and you ideally want them to be, in my view, paramagnetic. And that is what aluminium and tungsten are. So, and with high conductivity. So they're unique elements in the periodic table. And of course, tungsten's impractical. Aluminium is the third most abundant element in the Earth's crust. So that's kind of how the genesis of that was. But instead of flat plates, in the case of Eagley's device, it's two tubes. So you've got a tube and then another tube with the ground edge. So it's got a finer edge on it, but it has lots of emission and strike points that can be produced. Okay, so this was going into the samples, and you can see you have polonium-210 right at the back. You have cobalt-60. Now this unfortunately is one of the, this is ferromagnetic, then strontium-90. Some of these are paramagnetic. So they will be capturing or stopping potentially the charge clusters. And we went through a series of calibrations to get the calibration rate for the count rates for the various samples, whether they're gamma or beta activity. and then we ran the experiment, and in total the experiment ran...
Sparks here.
That's fine. Kill the audio here. In total, the experiment ran for about 12 minutes. I'll show you why, which I've not revealed before, but I'll show you why it only ran for that in a little while. But that's what we had to do. And in fact, that yielded this result. Okay, so first off, this is the after file sample averaging. This is the original level. So in the case of polonium 210, which is the one right at the back behind the cobalt, it was 8,483 times faster based on the 12 minutes of exposure. In cobalt 60, it was 7,710. The strontium 90 is 330,000 times faster decay rate than natural ratio. 330,000 times faster than natural ratio. Strontium 90 was the one tested in the Soviet hydrowave technology by the people that had run out of biological and chemical weapons to destroy in response to Kladov's work where he looked at cesium-137. And so they found that they could rapidly reduce in this system. Now, the special thing about the hydrowave technology is it has water flow coming through a arc. I think it's a tungsten electrode arc. That will produce atomic hydrogen, oxygen, OH radicals, and HHO. Okay? It will also produce intense cavitation. So you will have these hydrodynamic vortex structures with all of the components of HHO, as I have shared from the 2003 data study of the cavitation electrolyzer that is the Roy Shinomasa gas generator. Okay, and then that comes into a stator and a rotor, which are cut with annular rings, which go, or radial rings, which go, I think, in a golden ratio decay from a wide oscillation to a narrow oscillation as it goes out. So it goes, okay? And so you get all of the cavitation frequencies as the water gets thrown out with the rotating rotor on the stator. So you have the additional atomic hydrogen, protons, hydrogen, OH minus, hydroxide, and cavitation going on, and then into this cavitation system. So it's not surprising because it's got both this electrolysis, HHO, all of the above that does the magic, which we've identified over these years. Okay, so they verified, sadly, after Kladov died in 2003, it was in 2006 and 2009 in two different hydrowave devices. And in fact, I've said this before, when I was looking to make the proposal to 9 Sigma on behalf of TEPCO and the Japanese government, 9 Sigma operating then, but unfortunately it turns out they were not playing above board. But anyway, that's it. I was told by Dr. Alexander Parkhomov, well, look, if you just want to clean up that radiation, why don't you just use the hydrowave technology? Okay, that would be great if we had access to it. Okay, and this is the point. We need access to real technologies. Okay. And so cesium-137, that was decayed at 53,434 times faster, and thallium-204 was 79,808 times faster. And of course, it had to go through the carbon, and I will be sending the carbon off to the beamline at some point to see if that was aged at all. Okay, so I suspect that some of the paramagnetic nature of some of these materials prevented something going through here. Maybe strontium-90, I haven't looked it up. I could probably look it up now. If it's paramagnetic or not, I don't know. Offhand, I should probably done my homework on that. I'll do it now, and then I won't have to do it again. Yes, it's weakly paramagnetic. Okay. So if that is weakly paramagnetic, then the strontium-90 might be grabbing stuff, and it might be the case with cesium and stuff, so that by the time you get through to the polonium and the cobalt even, that quite a few of the charge clusters have been captured by the metals in question. Okay, so this is why I want to do another experiment where we take these samples, we do longer calibration tests, and we do another experiment, but this time with Griffin Brock witnessing it, because he made this device. Yes, it was my suggestion that potentially it could do radiation remediation, and I do have some issues with this experimental data because there are challenges. Unfortunately, it only ran for 12 minutes before sampling, and so we need to do more sets. But there was carbon at the front, and this could affect the process. So again, need to do it individually. Position on the radiation sensor. If I'm looking at beta particles, I need to actually saw out the mesh there to maximize that. Only did the pre-sample once, post-sample 5 times, and so on. So there's a few questions that need to be raised. But I have something very exciting to announce along these lines that will happen tomorrow, and that will lead to another series of things happening. But we'll come on to that presently. Okay, so back to the abstract here. Later, Parkhomov showed evidence that matter over 1000 degrees C in the presence of hydrogen or passing through water, or the radiation passing through water, could produce a kind of radiation that would also trigger reactions at a distance. Yul Brown reported radionuclide deactivation using oxyhydrogen plasma in the 1980s, and more recently Klimov, Anatoly Klimov, reported reduced detection from a gamma ray source in the locality of a hydrogen-oxygen plasma vortex reactors for up to 2 days. Now, this is why I want to know that I suspect it could be either remediating it or suppressing the ability of the gamma or the particles to be produced. And that's what I want to separate here. Now, in the case of Kladov, and in the case of the hydrowave technology, and the case of Marza, it genuinely got rid of the radiation. In the case of Klimov, he had these 2 samples, these big samples, and they're firing their beams at each other, and they produce gamma, and he saw that this gamma radiation was suppressed for 2 days. Okay. Kladov and Omarza observed radionuclide deactivation in water cavitation systems, the former having the observation verified posthumously using the Soviet hydrowave technology. Okay, so I've just talked through that. The conversion of cesium-137 into barium-138 has even been achieved biologically in water-based medium by Kornilova and Vysotsky. We will present new data from 3 experiments exploring technology for the rapid deactivation of radionuclides, including a new non-contact method derived from understanding the above observations. These simple-to-repeat observations could form the basis for energy-enabling practical technologies. What do I mean by that? Well, fusion. If anyone makes fusion, there's going to be some hot products produced. Okay, that's one thing. But we do know that, and I think even it announced this week, that the US Navy are going to be taking naval submarine and naval aircraft carrier reactors and installing them on land. I think that's the first time. Now, I'm not so sure about this. I'm not certain, but I was under the impression that those reactors use much higher percentage of uranium-235 in them, but it might be a completely different fission technology. Okay, whatever. The point is that if they are fission technology, they will be producing radioactive waste. And there is a massive investment gone into this company on making nano reactors or mini reactors. It was on the Sean Ryan show the other day. Billions and billions that have been raised to fund that, to make these small nuclear reactors. Okay, and there's been an agreement with this technology transfer with, I know, the UK. And so there's a large thinking towards doing a lot of at least fission, and there are also these investments into fusion. So it would be very good to have practical solutions ready and waiting for remediating the increased amount of nuclear radioactive isotopes that are produced. And secondly, also to give confidence to the communities that live near these things and to the wider public that there really is a solution. So if we have a technology where, and this is what I imagine, you have a bank of these Griffin-Brock tubes and they're able to go over the ground, you could decontaminate the ground, you could decontaminate reactors, and so forth if there was any potential accidents. And so that is where I'm trying to get ahead of potentially any bad stuff that happened. Okay, so with that said, those were the things there. Okay. We'll go back to here. So what happened that shut down our ability to do that? Well, it was this. This is the Brock tube that we were using that day, and I noticed after this 12-minute segment that it had started to mirror inside. And moreover, what I found interesting when I looked into it were these little spidery thread-like tracks. Okay, so the electrodes here, and I actually handed this this tube to Griffin, and he said he'd never observed this phenomena. He'd never observed this phenomena. Okay, but what we can see are these spider web-like tracks that are kind of like seem to be threading away from the main electrode here. There's this kind of like flying saucer type shape here where this electrode is. Like I say, Griffin says the vacuum seal had not broken. This is not a crack. So this is what we see. These look like networks of filaments that I've seen in Matsumoto's work. They look like they're traveling together and then merging up and then traveling together. And for me, this, given that we know that this has typically on its front face, it has this magnetohydrodynamic structure and it is producing these energy clusters, that these might be a whole series of them gone wild. Don't know, but I look at this from several different angles. You can see here, over here. Now, he did say that sometimes the metal has magnesium in it, and sometimes that can vaporize, but this was the first time that he had witnessed this. Right. Justo Mimo says, found similar in cathedrals, churches all over Europe. Okay. So, I took a very long diversion to actually meet him, and went down to Los Angeles to be able to meet him and hand over the equipment that he had loaned us to do these tests, and also pick up a bunch of extra tubes and also get an agreement with him. So what we found was, because of the import duties and the cost of shipping, it's like $175 for one of these Brock tubes, but then it's like nearly as much for the shipping, and then they want to charge you import duty on what it is, and also on the shipping cost and the VAT. And so it ends up costing more than twice, I think like 250%. By the time you actually get something in your hand, it costs 250% of the cost that Griffin is selling it for. And then you've got to make a thing to drive it, okay? So, and also that takes time. The shipping takes time, and it gets trapped in customs. And there are ways around these that I've learned more recently. You pre-authorize it for release from customs and so on. So you can smooth that process. However, it's expensive, it's lengthy, and also they can get damaged in transit, especially on long distance, because people don't necessarily follow, oh, it's a fragile item, and they don't treat it well. Anyway, so what I said was, look, if we set up some people that need support for what they're doing and help the whole technology go forward, you sell the devices, but we build them under license. So what I did was an agreement for Paul Harris to build them under license. And Paul has great experience in producing vacuum tubes for his Therify and so forth. He's had decades of experience of producing vacuum tubes and has people that he works with and electrodes. And also, the Czech Republic is most famous for producing glass for a wide range of uses. It's famously produced vast numbers of vacuum tubes during the Soviet period with its company called Tesla. That's what it's called. It still exists. But it was all over the Czechoslovakian countries. Anyway, so essentially I managed to hobble that agreement together so that Griffin sells them, but when you would get one in Europe, when everything's set up, then it would be manufactured in Europe, and Griffin would get likely more money. But Griffin would, a lot of the time when you bought a tube from Griffin, because when I first mentioned Griffin, he had unimaginable numbers of orders. It was very shocking for him, and he was physically making each one of these devices. So this means that he can start leveraging his IP, maximizing the number of people that can research using these devices. And so this is part of what the MFMP's original goals were, is to assist any application of these technologies in whatever their form. And this is the third goal. So we're really starting to get into the third aim of the Martin Fleischmann Memorial Project, and it's really wonderful to be here after all these years. And so to that end, Paul Harris made the first go at making these little driver structures, and he made this rather beautiful little box here, and he made his little variable capacitor here and his inductors and so on, but that didn't really work. And so Jan Rack and his team at the Elia Foundation in Prague have done incredible work, absolutely incredible work. We've had weekly meetings pushing this thing forward, and it would appear, Griffin is looking at a different type of driver system that's using a mercury-based suppressed spark discharge. It might actually be the magic of the spark that makes this work. But anyway, this was an early prototype that was done by the team at Elia Foundation, and this was actually demonstrated to people at the conference we did here, the Alchemy of Prague in 2025. And I'm going to play it here. I'm going to turn the audio on so you can hear it. I'm going to bounce it with a different mic here. So just give me a second. It's just easier to do it this way. Turn the audio on. Okay. Okay, I don't know. It's my panel here is saying there's a problem with the stream rate here, so I don't know what's going on with that. Can you still see me? No audio. There was no audio. Okay. Probably it just saw it as noise. It was definitely audio. Can you still hear me? It's fine now. Okay, no sound. Oh dear. Can still see. Okay, all right. Did you see the video though? Can you see what's on the screen here? This was the original setup that they tried. Okay, no, it's definitely here because I'm on Wi-Fi. Like I said, I'm recording it locally, so if there's an issue, then I will post it. Okay, hi Paul. Great to have you here. Okay, great. So I'll just play that through again. I'll put my microphone closer to it if that's going to help. It sounds like noise, so it might just be killing it. I'll actually switch it over so it doesn't kill the noise. Okay, it's killing the noise. It was killing the noise for some reason, so okay. Okay, so you saw it. Okay. Well, basically, this was the original one. It's come a huge way from there. And this long channel here joining up, this causes a problem, and that's been removed. You'll see that that isn't there in the original. But what I'm about to show you is incredibly exciting. Incredibly exciting. So first up, here is a compass. Now, the big challenge here, and I'm going to show you a paper that they're producing at Elia Foundation. They analysed it. They've been working with Griffin and Paul and myself to get the tuning, but really their expertise is fantastic, what they've done here to tune all the Tesla coils together and to understand how to tune it. Griffin's working on a completely different way to drive it right now, and this may be more compact. But what you're about to see is a real important watershed in this research. The ability to look inside things. So here we got a compass, a normal sort of compass you might have in the school. And it's in a packaging box with cardboard and this expanded styrofoam and polystyrene here. And here it is. Now behind this blue area here is the photo screen, and it's not got a very sensitive camera. It's got a GoPro in the back there, so it's not the best one. I'm hopefully going to go up there on Tuesday and we might be able to get some much better images. But this was the configuration, as you can see it. And here you can just about see this is the compass in here. But things have gone a little bit better because they got the tuning a little bit better. And here is a Logitech mouse here. And you can see a very clear image if I get my mugshot out of the way. This is on Open Broadcaster system. Get my mugshot out of the way. That's on the screen, so you can see here. And this is a close-up on the image. You can actually see the scroll wheel here. You can see the circuit board. You can see the lithium-ion battery in here. And this is a marker that they put on of a material that's very difficult to go through. Okay. So the question was from Paul and I, did you try your hand? And so Jan was brave enough to put his hand in there. I was putting it in quite a lot, so you can start to see the bones here. But the process, the tuning has got much better this week. And so Jan and Blanca, that's Jan's wife, have put their hands in, and we are now getting very nice real-time shadow graphs being produced. So I just want to say congratulations to the team at Elia Foundation and Jan Rack. This is absolutely fantastic. I want to put a real freaking good guys. Awesome work. Legends. This means why this is really important. Why? Because this is not only a replication of Tesla, it's a replication of Griffin Brock's real-time shadow graphs. But more importantly, Griffin Brock had only been able to get it to work with the 1920s diathermy unit. He didn't have a device that he had engineered himself. So this is actually better than a replication because a well understood electronic driving power supply has been produced that can produce these real-time X-rays. And that, my friends, is a boom right at you. Now, what does this mean? What does this mean? This means that the device that we were using to do the radioactive remediation up to this point in the last 2 weeks required someone to find a 1920s diathermy unit and get Griffin-Brock tubes, right? Now we have a situation where you don't need that. There is a well-described engineered solution to drive the Griffin-Brock tubes. And soon the Griffin-Brock type tubes and derivations thereof will be being produced in multiple locations under license from Griffin-Brock. This helps support the Elia Foundation. It helps support the work that Paul's doing. It helps support the work that Griffin is doing and his developments, and maybe even the MFMP can get something from it too to help our research. This is a practical application of the technology. And I have another thing for you tomorrow. Tomorrow, Jan Rack will be visiting. I would have gone, but I'm on the stream tonight and he's going in the morning tomorrow and it's up in Prague, blah, blah, blah. But it's going to be arranged later. They are going to try to attempt to replicate the radioactive isotope remediation initial experiments that I did in the US with Alan Goldwater at his Magic Sound lab. And this is in a nuclear laboratory with access to full isotopes. Boom! Double boom! So if we can, within a period of a few weeks, get replication of Griffin-Brock's real-time shadowgraphs in a way that is repeatable and engineerable, and many people around the world can explore it, and we get a replication of controllable radioactive remediation at a distance, we have effectively low-energy nuclear reactions that are switchable. At the flick of a switch, we can trigger remediation of nuclear isotopes. What a time to be alive. Thank you very much, Scialantis. That's very, very appreciated. What a time to be alive. And what an honor it has been to be able to meet these people, bring these people together, get these skills delivering. Now, something very interesting that Jan found and his team found, it gets better, in my view, because they did thermal imaging of the tube. And they found that at the end of the tube, when it's working, there is a hotter spot, which is nearly more than twice the temperature. Well, it's certainly hotter, okay? Certainly more than twice the background, 22.4 degrees. Of course, the emissivity is wrong and not necessarily perfect, but this is indicative. I've asked them to get some emissivity paint to ensure the actual temperatures are correct. But you have a hot spot here, you have a hot spot here, and the other hot spot possibly would be on the face of the electrode. And if that's the case, you might have a standing wave that's coming in here and a counter-standing wave coming back, which might mean that my intuition tells me that you are having the yin-yang, the magnetohydrodynamic structure forming on the electrode when the ion acoustic wave standing waves in the tube is in resonance such that it produces phase conjugation on the electrode. Okay, and what that will do is exactly what it's doing when you are producing phase conjugation and on a piece of aluminium foil in a ultra experiment. It's exactly the same process. And what that means is that it's not just you're trying to find the resonance of the tube will change its resonance as it changes its temperature. And what you want to do is to either control the temperature of the tube by preheating it, or maintaining it using a cooling system, or it has a particular radiative ability using Stefan Boltzmann, and you'll want to target a frequency that drives the resonance in there, and that will be something that will drive the most resonance and coupling between the input frequency and the emission of coherent matter traveling waves. Coherent matter traveling waves, these energy solitons. And so I think this little thing here, now he's not discussed this with me, and I've actually not discussed this with him, but I just wanted to make it public so everyone gets to hear it at the same time. So the ion acoustic waves in here, I think, are absolutely critical to the process. We may find that a flat tip on this might improve it, but I don't necessarily think it is, because what you're looking at is the tip of the ion acoustic wave will be here, but you might say that it's actually just it's a sound wave, so that might be critical to it as well. So maybe it would be better if it was flat, like the electrode is flat, to enhance the process. But anyway, this is excellent work from Jan Rack, and combined with these incredible images, full on respect to them. Yeah. Okay, so before we go on, I wanted to address something else. And I'm going to come back to what I spoke about earlier, which was, which I've now got in the blog, which is the commentary of Martin Fleischmann in response to George Miley. So I'm going to read the full thing here. So you can go and see the video. It's on the blog now here. It's actually been up for a while. Martin Fleischmann answers George Miley. He tells him what should be considered proof of transmutation. So what I'm learning from working on this video of Martin Fleischmann from 1998 is that he was self-deprecating, relatable, humorous, and very conservative in his proclamations. In the short questions and answers session after the presentation, he was asked the following question by the highly accomplished and respected lifelong nuclear scientist, Professor George Miley. Let's go and look at Professor George Miley before we go on here. This is Professor George Miley, still very much smiling. He is Professor Emeritus at Illinois University. He has a PhD in nuclear and chemical engineering, master's in nuclear and chemical engineering, and a bachelor's in chemical engineering and physics. He has had academic positions as Professor Emeritus in nuclear plasma and radiological engineering, University of Illinois, to present. Department Affiliate Emeritus Aeronautical and Astronautical Engineering, University of Illinois, to present. Professor of Nuclear and Electrical and Computer Engineering, University of Illinois, 1967 to 2011. Associate Professor, Nuclear Engineering, Electrical Computer Engineering, University of Illinois, 1964 to 67. Assistant Professor, Nuclear Engineering and Physics at University of Illinois, 1961 to 1964. So, since 1961 to the present day, he's been a very senior researcher in nuclear engineering. Other professional employment: President and Director of Research at MPL Associates, including incorporating Champaign, Illinois. Department of Energy, Idaho Operations Office. Clean Energy Technologies, Sarasota, Florida. That's where I will be next month. Edwards Air Force Base, California. Argonne National Laboratory and Los Alamos National Laboratory. Oh, click for more. Lawrence Livermore National Laboratory. Research interests: fusion energy systems, plasma engineering, low energy nuclear reactions in solids, direct energy conversion, nuclear pumped lasers. Nuclear pumped lasers. Books authored: Inertial electrostatic confinement fusion, life at the center of the energy crisis, Edward Teller medal lectures, principles of fusion energy and fusion energy conversion. Chapters in books. It goes on and on and on. This is a guy who really has done the rounds in the kind of fields that should be interesting to you guys out there. Professional societies, Fusion Power Association, American Vacuum Society, Society of Photo-Optical Instrumentation, American Nuclear Society, American Physical Society, member of Advisory Board for DOE Fellowships, Magnetic Fusion Technology, Chairman Technical Advisory. He was also member Oak Ridge Association. On and on and on. He was also the founding editor of Fusion Technology, a paper that one Takaaki Matsumoto published in until he mentioned ball lightning. I actually have in the Matsumoto archives, and I'm going to do a whole separate article on this, a attempt for Matsumoto to publish this synthesis of carbon and tubes in his cold fusion experiments in 1998. I have the whole correspondence, the submission letters, the reviewers' comments, and many of these documents are signed by George Miley. Actually signed by him, right? And in this correspondence, the reviewers are saying, well, Matsumoto didn't consider the carbon dioxide that could have been dissolved from the air in the water electrolyte. Now, the partial pressure of carbon dioxide is fantastically low. Basically, all dissolved gases of any real substance, of any real significance in water are nitrogen, oxygen, and argon. There's basically no carbon dioxide in the atmosphere. It's very little. And that the partial pressure means it's only that kind of ratio that could be dissolved in the water. That's one. Two, they say that the carbon coming out of the balls cannot necessarily be associated with the desynthesis and synthesis of carbon from whatever the atoms were. The point that they're missing in all of this is the size of the amount of carbon coming out here, or whatever these atoms are, but he says mostly carbon. In fact, what you actually find when you look at his analysis, and you will have all this in due course, is that he's finding carbon and oxygen, but you can't claim the oxygen because the oxygen's in the water. I mean, you really can't claim that. But it could be synthesizing the oxygen as well from the lead. But the volume of this, as we have observed in many of the things spewing out in the Benjamin-Wang reactor, is larger than the volume of the internal volume of this sphere. And that's what's so absurd with this back and forth, for me, with these reviewers. It's just frankly absurd. Anyway, you're going to see that anatomy of a failed review. And he also sends this off, I think, to Nature, and there's a bit of a review with Nature as well. So you're going to see the process that goes on. But bearing in mind, this was 1998. Okay, so let's go back. So now we have a bit of background of George Miley. Martin, I wanted to add my congratulations to you for clarifying so many issues. But what I wanted to ask you about, since you're talking about the future, you've left the whole field of transmutation out. What is your view of that? Well, I have to address Douglas Morrison here. Now, who is Douglas Morrison? Douglas Morrison was a famous CERN physicist from 1956 to 1959, and he born in Glasgow, but he was a major critic of cold fusion, and he really attacked. He went to conferences and did a lot of attempts to attack the whole research field. And this is where this is going to be interesting with the next document we're going to look at. I am an extremely conventional scientist. Now, people don't believe this, but I am actually a very, very, very conventional scientist. And when we got to March 1989, we had our singular result. And I said to Stan Pons, well, you know, you're going to have something with a proton, something with a triton. We'll never find that out. So, well, you know, the permutations and combinations of that, of all that's going on, that's horrendous. And yes, and partly this is because there are so many isotopes of palladium. Okay. And then everybody wanted to erect this enormous superstructure on this one point. Well, the outcome, of course, is predictable. It didn't work. That is, you couldn't erect this whole superstructure on there. So I'm sure that there's a great deal more than we haven't looked at. He says, I don't feel competent to talk about transmutations, but I've seen, well, George Miley got up and sat down. Where has he gone? My view of transmutation is if it was just based on profiling secondary ion mass spectrometry, I wouldn't believe it. But if you do isotope distribution, then you have to take it very seriously indeed. If you get the non-natural abundances of isotopes, then you have to take it very seriously. And, well, who knows? You know, Professor Takahashi here, he's got a three-body reaction. I think it's just that people believe that high-energy nuclear physics and everything was very simple. I don't think that's going to be so. Once you start shaking people up, they'll come up with all sorts of strange new phenomena. I haven't answered you very well, he jokes. I think if you have a distribution of isotopes which are not natural, then you really have to believe it. Okay, so that's what he said. Now, in my personal journey, I referred to George Miley many years ago, back in May 2018, 8 years ago. I did a presentation. It was published on the MFMP YouTube channel, and I published it on SteamIt that I was publishing on at the time. It was called What Really is the Nuclear Fuel? And in that blog, I did a composite image of a study that he had done that was reported by the Space and Naval Warfare part of the US military in relation to elements that he had found. So these were the elements that he's found. This is from a 2009 Miley study, and I've highlighted his ones in red, and the green ones are the ones that we had found up to 2018 in analysis. Okay, so he didn't just start with this report, and it wasn't the end of his journey. So we're going to look at a few things now that refer to what George Miley did. But the first thing I want to talk about is this DARPA call for request for proposals. Basically, they're asking for technology that will amplify fusion rates in solids. Okay, and I don't really want to go through much of this. There's a bit of contention because Nature have got in on the game, and this is awkward because what they're claiming is this 0.2 eV, and Matthew Villatte has this is 2000 degrees Kelvin, and of course we know 2000 degrees Kelvin is about 1000, let's say for argument's sake, 1700 degrees centigrade. We know that at 1000 degrees centigrade, according to the work of Dr. Parkhomov, you start producing these relic neutrinos. They can cause reactions. But anyway, this 0.2 eV has been found in beam experiments by by Konrad Chersky and other researchers, such as my former co-director Matthew Villatte in Szczecin in Poland, to increase reaction rates. Now, I don't know how practical technology it is, more than theoretical, but this has very much annoyed them that they're not being considered when they actually have demonstrated this in their experiments. But anyway, it's not that that's really awkward here. It's this. Unfortunately, solid-state fusion research has been marred by bold claims that could not be replicated. Okay, all right. Bold claim. Bearing in mind, the date on this publication is basically December the 30th, 2025. Okay. the fact that you have this idiocy by the US military here, and who are they referring to in 6? Oh, Pons and Fleischmann, 1989. Really? Really? What I just showed you is in a presentation at which George Miley asked the question and the response was given, I am a very, very conservative scientist. In 1998, right? We have this claim that they were very bold claims that were not replicated. Well, I'm going to show you that George Miley did replicate them at Hokkaido University with Professor Martin Fleischmann. I don't know. I have no words for this other than bleh, bleh. Come on. The US military can do better than this. They can really do better than this. Okay. So before we go there, I'm going to refer to a couple of things. Miley has been doing this transmutation thing for a long while. He's been doing it for a long while. It wasn't just what I shared from that presentation in 2009. I'm gonna share a couple of things here, and you're gonna see that this is not. It's not a story that's just happened. Okay. Okay. So there's no bigger story in transmutation, really, than the work of Stanislav Adamenko at the Proton 21 lab. And you can go and look at this at proton-21fusion.com. That is the lab in Kiev in Ukraine. And you can see on there that this paper here, published in 2015 in Results in Physics, okay? And this was when someone found 4 million and took the entire lab from Ukraine and parked it in Illinois. Who's in Illinois? That happens to be George Miley. Yes, this George Miley here as an author on this paper with the authors of this technology here. And you can see it goes on, but it didn't stop there. So basically they have a 300 joule capacitor bank. It dumps as an inductive charge into this metal rod, and then they break this plasma bridge here. So it causes the instantaneous discharge through this spark gap, which increases the rate of discharge, and then that goes through a dielectric barrier discharge and into the target. And the target typically is a little metal sample. Often they used copper. And here is the accumulating screen, which is also extremely pure copper. And you get this dielectric barrier discharge through this alumina based on the breakdown of the dielectric. And so it enhances the disruptive discharge, which literally messes with the ether. And that focuses into the plasma focus, or the electron focus goes into the tip of this little electrode here, and it blows up and it splays out all of its material around a sample here. And I think they did 20,000 experiments, sequential, that produced every element in the periodic table from every single element. Okay? And here is a typical example. So here, this is where the metal target was. And this is the accretion disk. At the same radii over here, you have one sample point, and the same radius over here, you have a different example. And they are thrown out from the explosion of this target. What do we get? Well, you have one sample here and one sample here. And B and C. What are the elements in B and C? Well, obviously they both got copper. But this one over here is copper and lead. And this one over here is copper and iron, right? Now, to me, that means that this coherent matter wave cluster was at the density of converting its copper load into a lead, and the coherent matter wave density of this one was converting its copper load into iron. Okay? This tells me that this can only be a coherent matter wave process. Mass collapse. Right here. This isn't all of the elements in the periodic table in this particular blob. It's a blob that's mostly the starting material and lead. And then mostly, in this case, mostly the starting material and iron. Okay? But over an analysis of the whole plate, you have all of these elements from your copper. Plenty of sulfur, plenty of aluminium, plenty of silicon, we've got plenty of whatever, all of this. Lovely. Okay? Blah, blah, blah. But he didn't stop with this in 2015. No, my friends, this one here is from 2021 in Physical Review Accelerators and Beams, no less. And here we go. Got all these chaps here. So Albuquerque, where I guess that's Voss Scientific, but Albuquerque is right next to where Sandia Labs is, and Sandia Labs is where Jan Rack used to work. Novikov, Usilov, Weller, Proton Scientific Technologies, Oak Ridge, and of course George Miley. Here we go. How the diode operates. Again, we see these things. Here's the experiment you can see. Super pinch diode. They call this the Thunderbird electron beam accelerator. Thunderbird. Oh dear. And they're doing the energy kinetics in there by exploding a piece of nylon or something here. This is the target here. But I think they've got like a... Anyway, he didn't stop there. Okay. But he didn't stop in when he asked the question in 1998. He's still publishing papers on transmutation. So transmutation is 100% real. It's over. But let's go a little bit back in history to look at one of his other papers. This you can download from the lenacanna.org, and I'll give you a quick link to that in a minute. It's called Review of Transmutation Reactions in Solids. George Miley and P.J. Shrestha, Department of Nuclear Plasma and Radiological Engineering, University of Illinois. Okay? It was the 10th International Conference on Cold Fusion, 2003. Okay? Right. A variety of low-energy nuclear reactions, LENAs in solids, have been reported. The original Pons and Fleischmann cold fusion reaction involved DD fusion. But instead of following the normal DD reaction channels, the intermediate products for helium was de-excited by energy transfer to the lattice that results in heat. Table 1, also transmutation reactions have been reported that involve an interaction between the D or H with atoms in the host lattice, typically heavy metals. In some Pons and Fleischmann type experiments, the tritium branch rates have been enhanced, but here we concentrate on reactions involving the host metal elements. This is specifically about transmutation. Types of transmutation reactions. Transmutation reactions can broadly be classified according to their characteristic product. Some experiments give a large array of reaction products with mass numbers spanning across the periodic table. The reactions are traced to multi-body events. Multi-body events! Yes, this is not collisions of particles, this is multi-body events, leading to the formation of heavy compound nucleus, which can both decay and fission into an array of elements. What is that reference to? Reference to, where are we? I'll be interested to see what that is. I don't even know. Oh, it's George Miley and Patterson. Reference to is himself. Okay, but here's the thing. He's literally saying what Matsumoto Can you hear me now? Oh, God. Can you hear me now? Oh, dear. When did you lose me? Can you hear me? Okay, all right. I've switched microphones. Okay, I'm so sorry about that. Okay, what did you miss? You didn't have to hear me swear. Good. You could read my lips. Okay, what did we miss? 2 minutes. Oh God. All right. Basically, I was talking about George Miley and essentially low energy nuclear reactions. But in summary, the most important thing is here is he's saying that he's not focusing on the DD fusion, but he's focusing on the reaction between the D or H and the host lattice. Okay, typically heavy metals. And he's saying transmutation reactions can broadly be classified according to their characteristic products. Some experiments give a large array of reaction products with mass numbers spanning across the periodic table. Okay, so this is in 2003. You have George Miley, lead author, saying that basically this is real. And there's no more person that I would respect on the subject of transmutations, given his experience, than him. And this is what he goes on to say. These reactions are traced to multi-body events leading to the formation of heavy compound nucleus, right? This is exactly what is claimed by S.V. Adamenko, which he would have been exposed to at this point. And of course, he was already exposed to, because I know he was exposed to, because he's literally writing to Takaaki Matsumoto. And Matsumoto is talking about many nuclei transmuting simultaneously. So 100% he has accepted the logic of many body reactions, which can both decay and fission into an array of elements. And this is referring to his own work, actually. The second reaction class leads to distinct isolated products. These reactions may or may not involve multi-body reactions, but the net result is direct formation of products versus the disintegration of a compound nucleus. Okay? Direct formation of products. What could possibly do that? We will first briefly review, anyway, so he then goes on to show some data similar to the data that was in the 2009 thing that I referred to earlier. Here we've got a lot of iron being produced, a lot of nickel being produced, nickel and copper. We've got a lot of lead being produced. This is observed by pretty much everyone that does this long enough, but S.V. Adamenko, it was in every sample basically. I think this is somewhere around about tin. Tin gets produced, it's like halfway between the two. You've got obviously carbon here. I think this probably is. Yeah, it's probably carbon. And these are typically things like magnesium, aluminium and silicon. And you're going to have sulfur around here, whatever. So yeah, it's typical transmutation products. We see these in our own experiments. And actually this is their own observation here in Cosima. Okay, but it's this table I found fascinating because I just thought let's approach this from a coherent matter nuclear reaction perspective, and let's see what we get. Okay, so I won't go into all of these things here. He's even referring to Hal Fox here, and Hal Fox is promoting Ken Shoulders. Here we got Shoulders 49 here. So here we go. Dash et al., Mizuno, and others have reported finding transmutation products in small regions around volcanic-like surface structures. Others, e.g. Miley et al., have not observed this phenomena, although such structures have been found on some of their electrode structures. How, or if this phenomena is connected to the reaction process is unclear. Shoulders, 49, Fox, and Baraboshkin associate it with possible electron cluster formation, which they view as driving the reaction. In contrast, Miley views the volcanoes as reactive regions where reaction conditions are highly favorable, possibly related to nuclear reactive regions, postulated by storms. So, we have essentially replicated shoulders. We have we're going to be replicating storms. And I think Miley is wrong. I think Shoulders and Fox are correct, causing extremely violent reactions rates that cause local melting before being extinguished? If so, thin film surface conditions created by Miley et al. Experiments appear to create reasonably uniform active regions over the surface. This is partially confirmed by SIM surface scans of key products such as copper, which were generally uniform within plus of 10 -% over the thing. Okay, right. Okay. I'm going to look at this table. We have Mizuno, Miley, Amori and Mizuno, Chernoff, Amori and Mizuno, and Amori. Different experiments. The production of potassium 41 from well, it's exactly the same ratio. So potassium 39 disappears and potassium 41 appears. And it's like this goes down by 21% and this goes up by 21%. I don't know whether that's normalized or what. Average value from the reference paper. Okay, anyway. This one goes down, that one goes up. Copper goes down by 30. This one, up by copper 63 goes up by 30. Copper 65 goes down by 30. Again, down here, up here. Down here, up here. In this case, iron, down here, up here. Down here, up here. Down here, up here. In the case of rhenium, up here, down here. In the case of silver, down here, the heavy isotope. Okay, so what we're going to do is we're going to use Brian's version of the Parkhomov reaction tables and see if we can emulate this data from a coherent matter point of view, where we are looking at multi-body reactions between a coherent matter wave of deuterons or oxygen and the host metal. Okay, here we go. So, review of transmutation reactions in solids, George Miley and Shrestha. This is the link if you want to go and get it. And I am suggesting that these reactions could be explained by coherent matter wave of a deuteron or oxygen interference in the core with the element isotope coherent matter wave. Okay, so let's take this one. 39 potassium to 40 potassium here. This one goes down. This one goes up. Let's have a look. We run this equation in the calculator, and what do we get? We get a first reaction with deuterons, they're in the material, and potassium 39, the most abundant element isotope, and it goes to a proton and potassium 40. Okay, but potassium 40 is radioactive. I don't think this occurred. I think two of these, two deuterons and two 39K, go to two protons and that should be in brackets. Should it be in brackets? Okay, I might have got the equation wrong there. It needs to be, 2D plus 39K goes to 2H plus 41K. Okay, I'll fix that. Idiot Bob. Okay. Let's try that again. I think I'm right in saying two deuterons plus 39K go to two protium plus 41K. So essentially a coherent matter wave of the most abundant deuterium isotope, which is just deuterium, interacts with the most abundant isotope of potassium, which is 39, yielding a production of potassium 40. And consequently, you get potassium 39 going down, and you get a non-natural isotope ratio being skewed towards, right? This is exactly what was said by Professor Martin Fleischmann in that 1998 interview. This is a non-natural isotope ratio because this one is going down, the most abundant isotope, and this rare isotope is coming up. It's not the most rare. Potassium 40 is the most rare. Could it be because it mostly goes this way? Okay. Next. You can have reactions with oxygen. Well, reactions with oxygen are most likely, well, there's no oxygen 16 in here, so we first have to create oxygen 17. Well, we know we can create oxygen 17 from interactions of protons, electrons, neutrinos, and oxygen 16, and we know that we can produce it possibly from a deuteron interacting with oxygen. 16. Anyway, you need oxygen 17, and it goes to oxygen 16, potassium 40. And again, you have oxygen 17 with potassium 40. So it's the same kind of thing, but the carrier is the oxygen. Okay? 65 to 63. Now, in contrast to this, the potassium 39 goes down, the potassium 41 goes up. In this case, the heavier isotope goes down and the lighter isotope comes up. How does that occur? Well, deuteron, coherent matter wave, interacts with the coherent matter wave of copper 65, and it ends up by producing helium and copper 63. That is the reaction that's available. You do need a neutrino involved. It's high energy though. There are oxygen reactions where you can have oxygen 17 and that goes through to produce nitrogen 15 and copper 65. There we go. Or oxygen 18 and it produces. So in all of these cases, the reaction that works is the one that eats up, in the case of deuterons, it eats up the copper 65, leaving copper 63. Okay, that would explain that. So it is, according to, as Miley says, interaction with deuteron. In this case, oxygen 17 is eating up copper 63 and producing copper 65. So in this case, it's kind of more likely to be the deuteron that's doing the work, okay, rather than oxygen. Okay, on the iron 56 to 57 to 58, if you take a deuteron, goes with 56, comes to 57. So 56 goes down, 57 goes up, 56 goes down, 57 goes up, 56 goes down, 57 goes up. In this case, it goes on to 58. Well, if you take a deuteron and 57, it produces iron 58. With oxygen, again, it's the 17 that plays a role, going through 57 to 58. Interestingly, here, when you have oxygen 18 and oxygen 54, it actually produces iron 56. It's the only reaction with oxygen 54, and that might account for why you have a disappearance in the 54, and you have a difference in ratio between these two, because this is slightly higher. So I think some of the 54 is moved on towards 56. In the rhenium in this case, again, the heavier isotope is going down, the lighter isotope is being formed, where if you take a deuteron and you react it with rhenium-187, I'm not sure this is radioactive, but anyway, you get helium-4 coming out with the neutrino necessary, and the output is rhenium-185. With oxygen 18, the same kind of thing, the opposite thing occurs. So this is again showing that the oxygen in this case is not likely to be the most well, it is in this case where you have oxygen 17 interacting, you get the production of rhenium-185. So it's probably again the deuteron, but maybe the oxygen 17 in this case. In the case of 107 to 109, this is not radioactive. I don't know why Brian's got it in his tables. It's one of the couple of bugs I need to help him with. But anyway, the silver 109 goes down and the silver 107 goes up. Okay. So deuteron interacting with silver 109 produces helium and silver 107. Again, you need the neutrino on the right. I could go through more reactions here. You can again have the process with the deuteron interacts, producing the heavier isotopes and so on. So it's like a stepwise process, again with the chromium that's observed. Okay. So interestingly, these data sets presented in 2003 by George Miley across all of these different authors, including Miley himself, are explainable by the Parkhomov reaction tables. And I believe it's a coherent matter wave process that occurs in the fractal toroidal moment cores. And that is what I'm going to say about that. But George Miley did not finish there, did he? No. So we just looked at this paper by George Miley. Okay. Now I'm going to look at something that's a little bit more damning, given the nonsense that we see promoted by DARPA here. This nonsense by DARPA, they have the audacity to put out this tired trope that it was a bold claim that could not be replicated. Could not be replicated. How on earth can they say that when we have the Navy Research Lab here? This is, I think this is the writing of Matsumoto, May 7th, 2001. Okay. And who was this written by? This is called the calorimetric analysis of a heavy water electrolysis experiment using palladium boron alloy cathode. We have Melvin Miles here, another leader in the field, Martin Fleischmann, M.A. Imam. This is, just so I show you that I'm not releasing anything that's classified, approved for public release, distribution is unlimited, March the 26th, 2001. So, and where was this conducted? I don't know, let's have a look. This study involves palladium boron alloy materials prepared at the Naval Research Laboratory. This new material was developed as part of a collaborative program with NRL and Naval Air Warfare Center Weapons Division. Okay. China Lake, and was funded by the Office of Naval Research. Studies at Norquad showed that the best product reproducibility for excess power was obtained using the palladium boron materials. Why? Why boron? Anyone guess? Why boron? Anyone guess? Anyone guess? Anyone guess why boron? The experiment studies described in this report were conducted by Dr. Melvin Miles and New Hydrogen Energy Laboratory in Sapporo, Japan. Yes, this is where Dr. Takaaki Matsumoto was a lecturer and did his research. Dr. Miles received a 6-month appointment as a guest researcher sponsored by New Energy Development Organization, NEDO of Japan. This experiment was conducted in the special DEWA-type calorimetric cell, silvered at the top, and was developed by Drs. Fleischmann and Pons. The detailed analysis of the experimental data presented in this report was conducted by Dr. Martin Fleischmann. An independent method of data analysis developed by Dr. Miles while he was in Japan was presented in his NEDO final report. It shows similar trends for excess heat effect. Okay. So, signed off by Melvin Miles and Dr. Fleischmann. There we go. There's Melvin Miles, Dr. Fleischmann. The cathode for heavy water electrolysis experiment was synthesized in a process using elemental palladium and boron at the Naval Research Laboratory, Washington, D.C., USA. The electrolysis experiment, as part of the continuation of the work in the Naval Air Warfare Center Weapons Division, was carried out by Melvin Miles during his stay at the New Hydrogen Energy Laboratory, Sapporo, Japan. The experimental data is preliminary evaluation carried out by members of the NHE group. Okay, so basically, its volume of the electrode was a third, roughly, of a centimeter cubed, 20.1 millimeters in length, and 4.71 millimeters in diameter. It had 0.5% boron. Boron involved in a neutronic reaction. Okay, so boron is a wonderful neutron absorber. Okay, and it's good that it absorbs a wide range of thermal neutrons. Okay, now for me, boron's very interesting in my story because we, in our first replication attempt of Chelani in 2012, we did what Chelani was going to do next, which was to, he saw a positive thermal feedback with excess heat, and he thought, well, I can't use borosilicate glass because it starts to soften around 300, 350 degrees centigrade. So he went to fused quartz. He wanted to go to fused quartz to produce his reactors. And that has a melting point of over 1,700 degrees centigrade. So there's a lot of headroom there. So he wanted to do that. We did it first, and it didn't produce any excess heat. So I thought, well, what have we done? We've not replicated what he did. Let's replace it with borosilicate glass. So we did that. Matthew Villat did that. Ryan Hunt did that. And using that setup, we saw excess heat. And that was, we published that for the first time shortly after we started the experiment on the 12th of December 2012. Okay, thinking about that, it led me to believe that boron was critical and that something that we had observed coming out of the reactor was interacting with boron. I told that to Francesco Celani. He realized that he had an old reactor where it was using Maycore, because I said Francesco Piantelli was using Maycore in his Il Nuovo Cemento reactor with Ficcardi, and boron trioxide in the Maycore. And so I thought boron was very important. I then decided that other neutron absorbers would be appropriate. I used indium, for instance, in 2019 when I was looking at doing some experiments with Roy Shinamaza, because it's also a boron absorber, a neutron absorber, a thermal neutron absorber, but it's also a large proportion of it is a beta isotope. I think it's a double beta isotope. So I was doing two things with one stone there. But here's the thing. I'm not sure I've publicly disclosed this before. That is not because I've been hiding it, because I might have disclosed it before, but I have to do it now. There are other elements that are suitable, and I mentioned this to Anatoly Klimov, and I've talked about this bead of sweat coming down his face, and then the following day comes out to me and says, well, we only get COP of up to 2 in a plasma vortex reactors if we don't use something like boron, cadmium, indium, gadolinium, or something. And it's not because these are real neutrons, it's because they also interact with these neutral structures that come out, what the Russians call fake neutrons, what we'll call energy solitons or exotic vacuum objects. Okay. And it took me further 2 years to get him to publicly say this. I challenge him in 2019 at ICCF 22 in Zizi, and I say, look, there are people in this room that know how to get higher excess heat, but they're just not telling anyone. And I kind of like gave him the side eye. I finally got him to say it. And it was very, very interesting, because at that conference, I sat down next to Bill Collis. Sadly departed, died of cancer. Unfortunately, he ran all of the European ICMNS conferences up until the one that we had in Strasbourg last year, or the year before. But anyway, Strasbourg. And that was because he wasn't with us anymore. But the last one he ran, which I was at, which was that I recall sitting next to him, he said, Piantelli has given up his research, he's disassembled his lab, and Bill Collis said he went to the lab and he was, he said, well, you can take whatever you like and blah, blah, blah. So Bill Collis was going through the materials in Piantelli's lab, and he says, the strangest thing, and Piantelli didn't say anything, and I have no explanation for it, is that Piantelli had a sheet of pure gadolinium. Pure gadolinium sheet. And of course, at this time, I already knew that neutron interacting materials were suitable for capturing these radiation that were emitted. And I already knew that Klimov was using gadolinium to enhance his energy output from a COP of 2 up to about 10 in his plasma vortex reactors, like the ones that Engate are using. And the thing is that, like, I'm just going to read some numbers here. Boron has a cross-section of 3,840 barns. Specifically, that's boron 10. But a natural boron is mostly boron 11. And so essentially you have an overall barns, this is the unit of interaction with the thermal neutrons, of about 760. Cadmium, Now, the good thing about boron, and I'll tell you what it is in a minute, is it's how it interacts with the thermal neutrons. Cadmium that you just get off the shelf is 2,450. So cadmium has a much higher interaction with thermal neutrons. Hafnium is 104. Europium is 4,570. But gadolinium is 49,000. So natural boron is 760. Gadolinium is 49,000. Okay? Now the difference in between these two elements is when boron is interacted with a thermal neutron, it produces 7 lithium and 4 helium and a quite low energy gamma ray. It's 0.48 of a mega electron volt. So if you get an electron and a positron annihilating, they produce 511 kilo electron volts. This produces less than that. So it's 480 kilo electron volts. Okay, and it's only producing 1 photon. So that's much easier to shield than high energy gammas. So it produces 7 lithium. Now, 7 lithium is the most abundant form of lithium in natural lithium. It's like 92.5% or something of natural lithium. But here, a lot of people, when they talk about boron, they talk about the neutron-boron 11 reaction, which yields carbon-12, which is aneutronic. In fact, both of the reactions are aneutronic. The boron 10 reaction produces 7 lithium as it absorbs that neutron. And the 11 that's in there, which is the rarer isotope, will produce carbon. Okay, so I would expect that if they had analysed the electrode, and bearing in mind it's only 5%, 0.5%, half of a percent by weight, that actually means it's more by atoms, because palladium is fantastically more heavier than boron. Absolutely massively. So 0.5% boron by weight is, I don't know, probably, 2, 3, 4% by mass, something. I don't know. I've not done the calculations, but you can do the calculations. So it's a lot more percent by elements, actual nuclei. Okay, so I would expect that if there were significant reaction ratios, and particularly in so-called active areas where the reaction would occur, you would observe 7 lithium in the absence of 6 lithium. That would be highly unusual, okay? And that would fit the measure. But they don't do that, as far as I'm aware, in this particular experiment. Gadolinium, however, what gadolinium does when it gets hit by a thermal neutron is it actually produces, well, there's many gadolinium isotopes. In fact, one of the gadolinium isotopes is absurd. I mean, it has, what have I got here? Gadolinium 157 has somewhere between 254,000 and 255,000 barns. Okay, so natural boron has 760. This has 255,000 barns. Okay, so gadolinium is the element in the periodic table that you would want to interact with thermal neutrons and, in my view, energy soliton neutron structures. Okay, when a thermal neutron interacts with gadolinium 157, it produces gadolinium 158 excited, which decays with a gamma ray, multiple gamma rays. And the gamma rays can be quite high energy. If 155 interacts, it produces excited 156, which decays to 156, again with gamma rays and X-rays. They produce gamma rays, X-rays, and they also produce Auger electrons. So a whole range of high energy photons are coming out. And as such, I have suggested last night to Binchuan Huang that if he is really believing that in his cavitation system it's actually producing thermal neutrons, then he should insert some gadolinium foil into the areas of the reactor where he thinks it's producing the most thermal neutrons. And if he does that, he will easily be able to detect these X-rays, but mostly the gamma rays outside of the reactor being produced. If it's real thermal neutrons. If it's actually energy solitons, no, I don't believe you're going to see the gamma rays. You might see them if for some reason some elements are produced and they then do a secondary reaction, maybe. But if you pull out that gadolinium and you see transmutation on there, but you didn't see any gamma rays, then probably it's not thermal neutrons. So I've suggested he did that. So essentially what it's doing when it in this experiment here, where we have this electrode with palladium and boron, is it's converting the yield energy, which is 2.8 million electron volts. It's converting it to the kinetic energy, mostly, of the 7 lithium and 4 helium produced. Okay? And the little bit of gamma ray photon that comes off. So it produces heat. It produces heat that will go into the electrode and into the electrolyte of the reactor. Okay, so that is why you would put boron in there. Okay? Well, let's go and see what they found. And I have a couple of clips that I took out of this, so let me just see where they are so I can find them. Okay. In here they talk about that they, well, actually the money shot's all really at the end. Sometimes it's not the case, but it is the case here. They did see one other thing. Oh, okay. So I'm just gonna pick it out here. I don't know exactly where it is. It's on day 3. They found that the major unexpected difference for this palladium-boron electrode has been the observation of the development of positive feedback at a very early stage of the experiments. At a low current density and at a low temperature, it is obviously very important to establish whether this early establishment of positive feedback is a property of palladium-boron alloys, the one used in this study, or whether some other factor is involved. The marked increase in the rate of excess enthalpy generation at temperatures approaching the boiling point is probably due to non-uniform charging. Well, as you go over 70 degrees C, you start to get cavitation. Maybe that was what was going on. When you get cavitation, you start to get magnetohydrodynamics, because you can literally see it in the videos of Matsumoto. And when you get magnetohydrodynamics, it's not necessarily what you think it is. Okay? Anyway, they saw this positive feedback, so I think that's very, very important. But they summarized down in section, where is it? A11, let's get to that. Basically, this is based on the Icarus 4 reactor, which was by Fleischmann and Pons. And so this is a replication in 2001 of a Fleischmann and Pons reactor done by independent parties, although one of the analysis was by Fleischmann. Okay, A11, let's get to A11. Right, further comments and conclusions. This palladium-boron experiment exhibits all the key features which have been found in earlier work. These are, in the main, excess enthalpy generation, this is excess heat, in the early stages. Time is less than 2 days. This is due to adsorption of deuterium in the lattice, followed by, this actually should be, absorption, of deuterium in the lattice, followed by a build-up of the rate of excess enthalpy generation. The development of positive feedback, i.e. the increase in the rate of excess enthalpy generation with increase of temperature. And on that note, remember how I started out. Ivan Filimenko's reactor ran at over 1,000 degrees. In fact, 1,150 degrees C, or yeah, something like that. So that was his 1957 palladium deuterium oxide boiling water reactor. It was, or reactor, it was over 1,000 degrees centigrade. So as it gets hotter faster. You can see how that might work. A marked increase, blah, blah, blah. A marked increase in the rate of excess enthalpy generation at temperatures close to the boiling point of the electrolyte. A variety of examples of the phenomena of heat after death, i.e. maintenance of the elevated rates of excess enthalpy production following reduction of the current density, which may be accompanied by the complete evaporation of the electrolyte. Okay. So there we go. And this experiment went for a long time. I think it was ran for 70 days. Okay, so it's a pretty sizable piece of work, and they do have a diagram of what the apparatus looks like somewhere. It may be right at the end. They have all the graphs, they have all the data, they have the analysis, the equations on which the analysis was based, and I will share this. Here's the apparatus. Right, so they have a thermistor well here, they have a heater well here to control it, and so on. So you can have a look at this in your own time. But this is having a look at inside the Naval Research Laboratories replication using a electrode that was produced by the Naval Research, which replicated Pons and Fleischmann. And this was published in March 26, 2001. There we go. So the fact that they are claiming here it could not be replicated in December 2025 is utterly farcical when the military knows it has been replicated. Okay, just based on this one document alone. All right, so we have been able to use what I think this Griffin-Brock tube is producing is the Tesla etheric matter rays, which are neutral energy solitons. These are the same things that were coming out of a overdriven tungsten filament light bulb through water and into lithium fluoride, producing, would appear, excess heat. This is triggering Lena at a distance, and I believe by using judicious compounds at a distance we may be able to. So one, I wanted to see a replication of the shadow graph technology. That has been achieved, but it's gone one step further. Actual production from scratch of a newly engineered device to drive the actual tubes. Here, this is the intense paper that's being produced by Jan Rack and his team at the LIVESTREAM Foundation. So this is from January the 26th copy. It's being updated here. So this is very, very detailed. It talks about Nikola Tesla here and Griffin-Brock, and here we go. You can see in July 9, 2025, the Elia Laboratory entered into a collaborative partnership with G.G. Brock Laboratories, represented by Griffin-Brock, and with Quantum Heat CIC, the organization operating the Martin Fleischmann Memorial Project, represented by Robert Greenier and Paul Harris. The primary objective of this collaboration is to enable the replication of the 1A21 Desmotron tube with European Union, and to further develop and assess its potential scientific and technological applications. Okay, so we've got a memorandum of understanding to develop this, and you can actually go to Griffin-Brock's website here, and you can see right here on the top, it shows the Elia Foundation have replicated the effect, and they've got the working document that I'm just about to read here available for you to download on his website. But I'll just go through it with you here. So here's kind of like some old ideas of how to make it. And here's the circuit diagram that they are using. And so you've got, and so what I've tried to do is I have done my level best to ensure that this is all going to be in the open. And this is part of that process, so you can physically see this device. So replicating and being able to engineer from scratch the device to drive it, the Tesla Shadow Graph as envisaged by Griffin Brock, into a device that can be used in science exploration all over the world. Okay. 2, my hypothesis that it would do radiative remediation at a distance in a non-contact way, and maybe it's suppressing the radiation, or maybe it's doing it because I didn't get to look at those samples like 2 days later, or 2 weeks later, or a month later, or whatever. Maybe they went back to their long-term average. Okay, I don't know, but this is a whole blue ocean of opportunity. But the initial experiment is very, very, very encouraging. Okay, and because I think what we're doing is we're getting to the nub of these emissions that was found by and claimed by Ivan Filimonenko, although never demonstrated publicly, but he claimed he saw them. Okay, and then the next one on from that is how we can use these emanations to directly trigger, by like flicking a switch, the Lena process. And if we can achieve that, and achieve that on scale, it's absolutely phenomenal. It's absolutely phenomenal. Okay, it would actually be able to apply for this Mars process, right? Because they're looking at what's the name of the game? Mechanisms for amplification of fusion reaction rates in solids. If this beam out here enhances fusion rates in solids, we have done what is requested by DARPA. Okay, do you understand? Okay. So you've got all the equations needed to work out everything, all the equations you could possibly ever want to equate. It's all in here. You can see the various iterations of the device. Okay, the spark gaps, all handmade, you know, plumbing fittings, washers, and so on. Getting the coils tuned, various coils, how they're assembled. Here's the inductance, turns, form a diameter. So with this information, so you'll be able to make it yourself, or Griffin, Paul, Jan will be able to ship one ready-made. But there's some way to go before everything works and it works reliably. And there's a lot to learn, but it's going all in the right direction, which is quite nice. So this was looking at specific aspects of the frequency and getting it into resonance. So it's a deep document which is being developed as we speak. Okay. It's not short. it's big on detail and being precise. Okay, so on and on. We lent the project's spectrometer to them. They found that there was a particular spectrum from the tube that worked, and not that spectrum from the tubes that didn't work. So of the 3 tubes that I brought back, one was operational with a weak spot intensity on fluorescent screen, and another one was operational but did not show any shadows on the fluorescent screen, and one didn't work at all. Okay, so this was no good. Okay, so what we've got to do is understand what causes this melting down, and I talked a bit about what I believe is the ion acoustic wave, standing wave, may be very important to setting up the overall ability to produce the shadow graph effect. Okay, so you can see here in the document the observation of the hot spots in the device. Here is the early shadow graph by a piece of copper in the way. And so on. Okay, but now what you have seen is that not only can they produce X-rays of important objects that you might like to have X-rays of, like your mouse. It can also produce X-rays of your hand, and presumably I'll be interested to see later this week that with a better camera we get much higher fidelity potentially in these real-time X-rays. And Griffin has said that by putting magnets, or rather a coil around the tube, you can focus the beam, and maybe permanent magnets would deliver the same kind of thing. I've also thought of potential other ways to force that, and we'll explore those. But what I'm looking for, Griffin said it can go 1,000 feet, and this will allow us to scan the Great Pyramid through the volume of the rock in an extremely fast way compared to the scan pyramids method of using natural muon interactions, which takes an extremely long time with the stochastic nature of the Monte Carlo type scattering, producing an image. So yeah, that's kind of what I would like to do with this, is to get 2 drones and just scan the pyramids and produce extremely detailed images of what's inside, and settle the debate there. That would be absolutely fantastic. So there we go. Again, thank you to David Boutelier for taking what I had read from Vasileitos and Tesla's work and reaching out to Griffin Brock and setting up that initial transfer of the sample. I have to say, huge thank you to Jan Rack. This is going to be allow us to not only see inside things, but we will also be able to change the inside of things. And it's really it really is a new dawn. I mean, this is actual working technology, and what I will say is tomorrow the initial contact is going to be made with these nuclear authorities here in the Czech Republic, and hopefully in short order we'll be able to run a series of experiments, and then they will run as one independent replication, and I will try and do another series of tests with Griffin in California next month. So it's really exciting days, and so I have to say, well done, Griffin, for not accepting that Tesla was making things up. I mean, Tesla literally had shadow graphs as photographs. You can go and see them in, I think, Serbia. You can go to the museum there and you can literally see the physical shadow graphs. He's replicated those with his own shadow graph tube, and now it's a technology. It's a nascent technology. It's an early technology, and obviously we're going to look at the nuclear authority to also characterize the radiation that's coming off. So people say, is this damaging like X-rays? Maybe it is. For me, and I've said this to the guys, one of the most exciting things that could be a potential with this shadow graph technology is not just looking into things and changing the inside of things, and potentially triggering Lena with a flick of a switch. It could also do what W.C. Levengood did, having studied crop circles. An application of the rays from this into seeds could enhance their germination, and so this means that you could have seeds coming through a dose of this radiation, and they may exhibit the same properties of seeds treated to the expired patent of W.C. Levengood. So this could have implications for farming, for remediation, for medical applications, in terms of it could actually enhance blood flow, it could enhance regeneration rates. And so what are the risks? If it's not actually some form of real X-ray and it really is these energy solitons, Here's the difference between how an energy soliton interacts with matter of certain energies and a X-ray, to the best of my knowledge, and this isn't medical advice. When you are exposed to an X-ray, and as I've said before, my dentist's husband, who was also a dentist, died of breast cancer, right? And that's because they were exposed to X-rays during their working life. And in fact, his working life was cut short significantly by having breast cancer and dying. Okay, it's tragic. Okay, so the thing about X-rays that you have at the dentist, or when you've broken your arm or whatever, every single one of those X-rays can cause genetic damage in every single cell that they pass through. Every single cell that they pass through. Okay. Now, the thing about an energy soliton, as I appear to have demonstrated, is that they can remediate beta isotopes. Cesium-137, strontium-90, so on. Okay? Remediate beta isotopes. The beta isotopes that are in your body are carbon-14, which is 1 in every trillionth carbon-14 carbon atom. So if you take all of the carbon, you're mostly hydrogen and oxygen. Okay, almost the whole human form is hydrogen and oxygen. Okay, and there are 2 principal beta isotopes in your body. They are carbon-14 and they are potassium-40. Okay, potassium-40 is a rare isotope of potassium, and what has to happen is the energy soliton has to be of the right energy and to pass through, and in my view, the core of the monopole, or the topological monopole, or fractal structures thereof that are above a certain energy density, magnetic field strength, they will have to pass through the radioactive isotope to trigger its decay. And when that happens, in the case of carbon-14, it will decay to nitrogen-14 and emit a beta particle of a energy which could do some damage. And of course, if the carbon-14 is in your DNA, it will cause the DNA strand to be broken, but there are mechanisms that the body can use to fix those. And moreover, potassium-40 in your bloodstream, again, it produces a high energy emissions. However, it's only those elements and they are rare. Not every single cell that the photons pass through that are gamma. Okay, so relative risk, if they are not X-rays at all, my intuition is they are massively lower risk. On the flip side, because they are, in my view, energy solitons, and this will be determined, if they are actually energy solitons, they have the potential to massively enhance production of white blood cells and regeneration. So the net benefit could be much, much more positive than the small amount of change to rare isotopes in the body. But again, don't try this at home, kids. A lot of work needs to be done in the interim on biological samples. But I have a good feeling about it. And this is a real technology, and it is kudos to this man here. Thank you, Griffin. And thank you to the team at Elia for replicating this extremely important process. Right, if you've got any questions, let me know. And otherwise, I've got an interview tomorrow and I've got a meeting, so... I think on this, do not try it at home. We are in the process of enabling broad-scale research using this technology. Thank you, Jalapeno. Yes, this is really an important moment in the history of the project, really. Thank you, EVB2421. Yeah, thank you. Actually, I actually have this here, which you might recognise. It won't be a stream tomorrow. It's on the Higher Side Chats YouTube, and so you'll see it there. Yes, thank you, EBB. I've used it all winter. Thank you very much to you and your lovely wife. I want to say thank you to all of the donors tonight. Really, really appreciated. Thank you to Black Tie, regular. Thank you very much. Thank you to JB Beach Loves. Thank you to Algaz 2001. Very kind of you. To Siolantis, I think that says. And thank you to Follow the Rabbit Hole. I think I saw you on a video down in South America. Did I follow the rabbit hole? Was that you or was that someone else? I thought you were in the background. I might have misread that. Yeah, full credit to Eric Dollard. Eric Dollard has been really working and helping Griffin. So I think Eric Dollard helping Griffin Brock and Griffin Brock's determination and persistence has cascaded through to potentially extremely important technology that can make a profound contribution to the future of humanity. Oh, really, Marty Angel? Well, okay. Wonderful. Long time ago. Okay, it's quite late for me. I think I'm going to call it a night because I've got a lot to do tomorrow. I've got a comment from Alan. Okay. Ooh, I probably shouldn't have said that. Ah, okay. Ah, right. Remove from your memories. I need to phone Alan. He's telling me I shouldn't have talked about it. Oops. Oops. The big faux pas. Sorry, Alan. Sorry, Ed. Oops. Didn't know. Okay. Okay. All right. Okay. All right. I better go and speak to Alan. All right. Buenas noches, dobronoc. Good night.